In this module, we will continue with our discussion on the quantum mechanical treatment of a rigid rotator. As you already know, a rigid rotator will be basically a model for a diatomic molecule, and the energy which we will get, that will be the rotational energy of the rotator. A rigid rotator is called rigid because the distance between the 2 point masses is fixed at r, and the 2 point masses have their respective masses m1 and m2. Their distances from the center of mass are r1 and r2 respectively. In the last module, for such a rigid rotator model, we wrote Schrödinger equation, expressed Hamiltonian in terms of angular momentum operator, and then angular momentum operator, which was initially expressed in Cartesian coordinates, it was transformed into polar coordinates. And then the resulting Schrödinger equation which we got, using the method of separation of variables, we split that equation into two equations. One was the theta equation. Here theta varies from 0 to pi. And the second was the phi equation, where phi varies from 0 to 2 pi. So in this module today, we will continue from there onwards and try to solve these two equations and then ultimately get the total wave function for a rigid rotator as well as the total energy of that system. As we have already seen that the total wave function for a rigid rotator in terms of the polar coordinates theta and phi can be written to be the product of theta theta and phi phi. And we have also seen that the Schrödinger equation can be split into two equations. One was the phi equation. Here you can see equation which is the phi equation, and this is 1 upon phi phi, del 2 phi phi upon del phi square is equal to minus m square. And the other equation is the theta equation, which is sin theta upon theta theta, del by del theta, sin theta del theta theta upon del theta plus beta sin square theta minus m square is equal to 0. Here, if you remember, as we discussed it in the last module, beta is equal to 8 pi square IE upon h square, where E is the total energy of the rigid rotator. Now we will take each one of these two equations one by one and try to solve them. First, let's try to solve phi equation. The phi equation, if it is rearranged, we get the equation which is delta 2 phi phi upon del phi square plus m square phi phi is equal to 0. Now, for this equation, the general solution is phi phi is equal to n e to the power iota m phi, where n in this case is the normalization constant, and phi, as you know, varies from 0 to 2 pi. If we apply the normalization condition on this phi function, we have the set of equations which that the normalization condition means that they should be equal to 1, and if we further simplify, we get the value of the normalization constant n equals 1 upon under root 2 pi. And if this is substituted in the first above expression for phi, we get phi phi is equal to 1 upon under root 2 pi e to the power iota m phi, where m can have values from 0 to +1, -1, +2, -2, etc. And if you recall, in the last module, we had a similar equation for a particle of mass m moving in a ring of radius r. So please note that this phi, which is the solution of the phi equation, this is also the solution for a particle in a ring. This is very, very important. And further, you can notice here that if we have the value of phi beyond 2 pi, it will repeat itself. Suppose we have phi is equal to phi plus 2 pi, and then if we make the substitutions, then the value will come out to be the same. That means basically this m is varying from 0, then plus 1, minus 1, plus 2, minus 2, etc. At this stage, I would also like to mention that when we will go to the hydrogen atom, similar equation will come there also. And there, this m we call to be the magnetic quantum number. We will discuss it later on in the solution of the hydrogen atom. Now, after having solved phi equation, let's solve the theta equation. Equation, as we mentioned, depends on theta, and this equation is as it is shown here. Now, how to solve this equation? It is easier to solve this equation if this equation is transformed into Legendre's equation. Legendre's equation is a well-known equation, and which is of the form, as you can see here in equation, 1 minus x square d2 px upon dx2 minus 2x dpx upon dx plus L into L plus 1 minus m square upon 1 minus x square parenthesis closed px is equal to 0. Why do we need to transform into Legendre's equation? If theta equation can be converted or transformed into Legendre's equation, then the solution of the Legendre's equation is well known. Therefore, we can very well and very conveniently find out the solution of the theta equation. Now the question comes, how to transform theta equation into Legendre's equation? For this, we make the substitutions. These substitutions are shown in the equations. We put x is equal to cos theta, and therefore 1 minus x square will become equal to sine square theta, and 1 minus x square under root will become equal to sine theta. And as you can see, dx will be equal to minus sine theta d theta, and we make the substitution theta is equal to px. And then if we have to substitute anywhere del by del theta, this can be written in the form del by del theta is equal to del x by del theta multiplied by del x. This on simplification gives you minus sine theta del by del x equals minus 1 minus x square under root del by del x. You can see that if these substitutions are made, then this theta equation can be very conveniently and very easily transformed into Legendre's equation in the form as given in, and it will become exactly Legendre's equation if beta is substituted to be equal to L into L plus 1. This equation we will also encounter in the case of hydrogen atom later on. And if you remember, this azimuthal quantum number comes from here. Just as from phi equation, in the context of hydrogen atom, we get magnetic quantum number. Similarly, in the case of theta equation, L comes here, and L we know is called azimuthal quantum number. And we will discuss all these details in the solution of the hydrogen atom. Now, once theta equation has been transformed into Legendre's equation, then we have to see what are the solutions of the Legendre's equation. Solutions of the Legendre's equation are as written in equation PL absolute mx is equal to 1 minus x square raised to the power absolute m by 2 dm dxm, both m being absolute, plx. This is the solution of Legendre's equation. This is also called PL absolute mx is called associated Legendre polynomial of degree L and order m. And PLX in this above equation is given by the PLX is equal to 1 upon 2 to the power L, L factorial, dl upon dxl. Then in parentheses we have x square minus 1 raised to the power L. So we have the solution of the Legendre's equation. Here you can see we have given a table where for different values of L, we have the values of PLX. For example, P0x is 1, P1x is x, and so on. These can be used and these will be used later on while finding the solution of the Legendre's equation for various values of L and M. One needs to remember here that one of the conditions here is that the absolute value of M has to be less than or equal to L. That means the value of absolute M cannot be greater than L. Because why should it be so? Because you can very well see that if absolute M is greater than L, then the value of the associated Legendre's polynomial will become 0. But please remember that in the case while we transform theta equation into Legendre equation, we made the substitution x is equal to cos theta. Therefore, ultimately we will have to go back to cos theta. And therefore, now one can say that the solution of the theta equation is theta would be equal to NLM, which is the normalization constant, PL absolute mx. Now, what is the value of the normalization constant? This value of the normalization constant has been found out, and this is equal to, as you can see here, NLM equals square root of 2L plus 1 upon 2. Then we have L minus absolute M whole factorial divided by L plus absolute M whole factorial. So this is the normalization constant for the theta function. If we substitute it back, the ultimate value of theta function becomes normalization constant into PL absolute mx, where x is, as you already know, equal to cos theta. Now, by solutions of these two equations, theta and phi, we have been able to get the corresponding respective functions. But we need to find out the total wave function of the rigid rotator. And the total wave function of the rigid rotator, as we mentioned in the beginning, is psi theta phi is equal to theta theta into phi phi. Therefore, if these two functions are substituted in this equation, we get the corresponding total wave function. This is the total wave function of the rigid rotator, and this is equal to psi theta phi is equal to 2L plus 1 upon 2 L minus absolute M total factorial upon L plus absolute M total factorial into PL absolute mx. This is the theta part. Then multiplied by phi part, which you remember we calculated earlier, and that was 1 upon under root 2 pi e to the power iota m phi. So this total expression on the right hand side gives us the total wave function of the rigid rotator. Here one must remember, as it has been mentioned, L can have the values from 0, 1, 2, 3, and minus M will have the values between minus L to plus L including 0. That means M will have 2L plus 1 values. These wave functions or the eigenfunctions of the rigid rotator are also called the spherical harmonics. Please remember, this is very important. All these things we will be ultimately using in the solution of the hydrogen atom. Some of the wave functions of the rigid rotator for different values of L are given in this table. You can see first is the wave function for L is equal to 0, and then we have the wave function for L is equal to 1. You can see how it looks. Then we have the wave functions for L is equal to 2. For L is equal to 1 and for L is equal to 2, for different values of M, the corresponding expressions are given. So this is the list of the spherical harmonics. But please remember that for L is equal to 1, M will have the value -1, 0 and +1. And for L is equal to 2, we will have +2, -2, then +1, -1 and 0. After having obtained the wave functions, one needs to find out the total energy of the rigid rotator. And if you remember, we mentioned it earlier that beta is equal to 8 pi square E upon h square. And now we have shown here, while transforming theta equation into Legendre's equation, that beta is equal to L into L plus 1. So substituting it back, we get the total energy E, which is equal to L into L plus 1 h square upon 8 pi square I. Here L can have the value 0, 1, 2, 3. Sometimes in a rigid rotator, when you discuss spectroscopy, you talk about J instead of L, but the corresponding expression looks similar. In that case, it will become E is equal to J into J plus 1 h square upon 8 pi square I. Then J is called rotational quantum number. So, but values are the same. So in this module today, we have solved completely the Schrödinger equation for a rigid rotator, which is a model for a diatomic molecule. And in this model, the distance between the 2 point masses is kept fixed. That is why it is rigid. And it is rotating about an axis which is perpendicular to the internuclear axis and passing through the center of gravity of the molecule. We had split Schrödinger equations into two equations, theta and phi equations. We first solved phi equation and got the corresponding wave function. And we did mention that this phi function is also the solution of a particle moving on a ring, which we had discussed in the last module as well. And then we also solved theta equation by transforming it into the Legendre's equation, and we got ultimately the solution of the theta equation. The solution of the theta equation and the solution of the phi equation ultimately gave us the total wave function of the rigid rotator, which is the product of theta function and phi functions. And we also did the normalization for both of them and ultimately got the total wave function. Lastly, we got the total energy of the rigid rotator, which came out in the form E is equal to L into L plus 1 h square upon 8 pi square I, where L is a number which can vary from 0, 1, 2, 3, and I is the moment of inertia, which for a rigid rotator is equal to mu r square, where mu is the reduced mass and r is the distance between the 2 point masses m1 and m2.